But for now, to kick off the overall discussion, I'd like to introduce our guest speaker, Bill Brinkman, who's the Director of the Office of Science for the Department of Energy. Dr. Brinkman was named Director on June 19, 2009, and was sworn in June 30th, 2009. He has extensive biography, which I apologize I'm not going to read because I'm cutting into your speaking time. Significant history at Bell Laboratories and a number of other places. A brief explanation for those of you not familiar with Department of Energy Office of Science. Office of Science received in FY 2009 about $4.7 billion in appropriations. A primary role of the Office of Science is really the underlying fundamental science that will support energy infrastructure into the future. This is the arm of the Department of Energy that really focuses on science research. Some of that's funded to universities, some of it's to government laboratories, but it's the place where in many cases, some of the ideas that we'll be relying on for our energy and environment 20, 30 years from now are being funded and being thought about. So it's exciting to have Dr. Brinkman here, and we're looking forward to your comments.
Well, thank you and good morning. It's a privilege to be here and talk to this board about what we're doing in the Office of Science and in the DOE. It's an exciting time in many ways. As many of you know, Washington is in a turmoil at this stage, and while he cited my budget at $4.9 billion, there are people who would like to make it $4, and there are people who would like to make it $5.5. So heaven knows where it's going to end up. But it's an interesting thing. But I'd like to tell you a bit about the department and my organization. And we, as was said, we are the science wing of the department. It was the department, of course, derived from the AEC. The AEC, of course, managed the nuclear weapons program and the evolution of nuclear power into a practical source of energy, electricity over the 40s and 50s, and as you all know, physics was a real base of understanding nuclear fission, and so physics, basic research in physics and related fields was always considered to be a part of the Department of Energy. Today, the research organization is really at the frontiers of science. Over the years, we've gotten something like 100 Nobel Prizes, and 22 of them in the last 10 years, last decade. So we're still doing okay. And in that front, we are actually 45% of the total federal dollars in physical sciences. The others, of course, are NSF and DARPA and a few other organizations of that type. So we're a large part of the support of chemistry and material science, nuclear physics, and particle physics, all that kind of thing. We support like 27,000 PhDs in various ways. We support graduate students, undergraduate students, all working on research that we fund. In addition to that, we have created what I consider to be the greatest set of tools for analysis of materials and characterization of materials that have ever existed. We have built large synchrotrons at a number of our major national facilities, and these synchrotrons have had a huge impact on science in the last 10 to 20 years. And we have a total of 26,000 users that come to these facilities every year. So we're a really large operation. Not only do we fund these national facilities and at our national laboratories, but we also fund over 300 universities. And so we have academic institutions. We could probably find a dot for Lehigh on there somewhere, and a red dot. And the yellow dots represent the national laboratories. And there are actually 17 of them on there, but the basic science part of the 17 are 10. And you probably know of many of them: Oak Ridge National Laboratory, Argonne National Laboratory, Brookhaven National Laboratory out on Long Island, Lawrence Berkeley Laboratory in Berkeley, California, et cetera. And these are some of them are big multi-purpose laboratories which address a really broad spectrum of questions, and are very interesting places to visit. We've done a few things in the last year or two. I want to just mention this. We've created an early career award program, which we try to encourage young faculty, and we've started this up, and it gives, for universities, it gives $150,000 a year for over 5 years, per year for 5 years. It's a nice little grant that can help the people in their mid-career. And we've also been trying to do a graduate fellowship program, but Congress is just trying to figure out if they really like us doing graduate fellowship programs or not. So we have quite gotten there on that. But this program is very nice. We got 69's award and got it going. But what I come here today to talk about is not so much my organization as the whole issue of climate and what's happening in the climate world and how that relates to energy and what we're trying to do in the energy world. And I try to explain that. So I want to talk a little bit about climate. I think everybody knows this plot. This is a classic plot of the concentration of CO2 in the atmosphere. It has clearly gone up ever since, well, if you go all the way back to 1850, before the Industrial Revolution, it was another bit lower than this, but it's been going up at an increasing rate. And this is a major concern for all of us that this increasing CO2 in the atmosphere could have a negative impact on our climate and have very serious consequences. To give you an idea of the kind of consequences we worry about, this is, I think, one of the more clever experiments in the whole field of climate. This is an experiment called GRACE, Gravity Recovery and Climate Experiment. And what these people do is they take two satellites and they follow each other around the Earth. And they use an RF interferometer to measure the distance between the two satellites to less than 1 millimeter. And so these two satellites go around, and suppose you go tracking over this same path, and you come back the next time, and some of the ice underneath on say the Arctic, the Greenland has melted away. Well, the gravitational effect is not quite so strong there. So the first satellite sees that first, and it moves up a little bit compared to where it was the last time. You can measure that motion. And so you can measure the change, the total change in the mass of Greenland using this experiment. And it's a very beautiful experiment, in my opinion, that you can pull that kind of thing off. And they do all kinds of other experiments besides the directly climate-related ones. For instance, they have gone over the Mississippi Valley in the spring and in the fall. And of course, in the spring of the year, the Mississippi Valley is full of water, right? You know, it's the melting snow and that sort of thing. And by the fall, that's all dried up. And so you can see a huge difference in the gravitational pull of the Mississippi Valley just between the two seasons, right? And so here is a case where they've looked over and over again over the last 7 years at Greenland, and it's very clear that the Greenland ice cap is melting from this data. And the reason I like this data so much is most people go up to Greenland and they look at a glacier and say, oh my God, this glacier is melting. But we also know that there's a lot of snow going onto the top of Greenland, and how do you decide who's winning, right? And you can't decide who's winning by these things. But this thing is a total measurement. It measures the total gravitational pull of Greenland, right? And so you get a really good answer. But the interesting feature of this is these numbers over here. The same thing was done for Antarctica. And it shows you, for instance, that the rate of loss of mass in Greenland has increased from 137 to 286, which is a factor of 2 or so in only 7 years. In fact, only 4 years. And likewise in Antarctica, it's increased by a factor of 2. So this is rather clear evidence that there are some things going on here, right? And we can think of this as trivial, but if you take those numbers and ask, what does that do to the level of the ocean? Well, it's, I think, a couple millimeters a year. And so, so you know, 10 years you got 20 centimeters, right? And so 2 centimeters, and 100 years you got 20 centimeters, and that's starting to make me worry about my summer house at the beach. and so that kind of thing you have to worry about. And then you can have this enormous long argument about whether it's really due to increasing CO2 and whether human beings have been the fault of this increasing CO2. But at least one thing you can say is it is surely, the CO2 in the atmosphere surely has come from fossil fuels. And that's this next thing. It turns out that, that the atmosphere normally, if it just was a certain amount of CO2 in the atmosphere and on the surface of the Earth, the cosmic radiation would cause changes in the carbon and nucleus and create carbon-14 nuclei at a fairly high concentration. However, fossil fuels that are buried deep in the ground, those cosmic rays don't get to. So the carbon CO2 in the atmosphere, if it has a depleting amount of carbon-14, it is very clear evidence that this CO2 must be coming from fossil fuels. And this is what this shows. It shows 2 different plots. One is carbon-14, which is green, and you can see it dropping off very rapidly. And likewise, if you look at carbon-13, which is a little bit more complicated. An issue is how where it comes from and how it is depleted, but a similar story goes there, and both of them are dropping off, which is fairly strong evidence, in my opinion, that whatever else is true, our use of fossil fuels is driving the CO2 in the atmosphere at this stage, and so these arguments are, in my opinion, strong arguments that things are happening here. And it's true that when we look at look at what's happening in terms of global temperatures, it is true that it's been relatively flat for the last 10 years, and people have made a big deal out of that. But you know, if you look at it closely, and we add the last 2 years in, you see that relatively flat spot and a bit of a drop off is now heading back up at a rapid pace. And so I think it's very, very dangerous to look at short-term fluctuations. Look at that curve, and you look at this thing, and it's fluctuating all over the place. In fact, you can find other 10-year stretches in those curves where temperature actually went down, but the fluctuations are very, very strong. So you can have a big argument about this and try to argue that it's not important, but it seems to me that at least we have some real evidence that things are happening, and we have changed the nature of carbon dioxide in the atmosphere, and certainly it has gotten warmer, and those 3 things are true. So what do we do about it? Well, let's talk about global and U.S. energy outlook. What can we do to change the mix of what we're doing? And that's what I'm going to spend the rest of the time on. I'd like to see if we go through that. You know, if we do nothing, we're just going to go along this curve. And as the rest of the world starts catching up with us economically, we're just going to expand the use. And if you look what's expanding, coal is expanding the most, and nuclear and gas are both expanding, and I mean oil and gas are expanding, and so by 2030 we're going to be quite a bit higher in the total use of these energy resources that give rise to CO2. So we have a real issue there. You know, it's interesting. I sometimes say that the only change that has occurred in the whole energy business in the last 5 years is natural gas. And you're in the state of Pennsylvania here. I can't imagine everybody doesn't know a lot about that. And that is that we have changed with the advent of our ability to crack shale, to get natural gas out of it. We have changed the whole dynamic of natural gas. So the U.S. now has more natural gas reserves than Russia. which wasn't true just a few years ago. And in fact, we have more natural gas reserves than anybody else in the world. And so all of a sudden, we have a very different picture from the natural gas point of view. I remember I was on the committee for America's Energy Future 5 years ago, and when we started, we thought we were going to, our whole report on natural gas was going to be about building terminals for liquid natural gas tankers coming into the, and now we don't even use the one terminal we got. So it's an enormous change, and that's what you see with the unconventional natural fuel here. It's a big effect, but you know, and natural gas has the nice benefit of being a factor of 2 less CO2 than coal per kilowatt hour of energy, and so it's good from that point of view. But I will argue that a factor of 2 won't get us there. In fact, let's look at this plot. I don't know how many of you have seen this plot before, but this is a famous plot that was done a few years ago, and this sort of shows you where we are and in uses of energy. Various energies are listed on the left-hand side here: solar, nuclear, hydro, that's power plant, that's wind, geothermal, natural gas, coal, biomass, petroleum. They add up to about 100 of these things called quads, and then you can see how they're divided up and what they're used for. Coal, of course, predominantly, almost entirely used for electricity, although some industrial processing. Solar is used for electricity, what little bit of it there is. But petroleum, of course, is divided between industrial uses and you know, industrial uses being plastics and all the other things we make out of petroleum, and then, of course, transportation. And one of the things you might want to note is that if you look at this, this adds up to about 100 quads, and the actual used energy adds up to about 42 quads. So the whole industry is around 40% efficient, and some of them are better than others. I mean, if you look at transportation, petroleum down there, you start out with 26 quads, and you end up with 7, which is not even 25%. So you have a varying amount of efficiency that you'd like to deal with in this kind of thing. So anyway, this is the picture of what we're doing, and if you rewrite it in terms of CO2 emissions, here's where it comes from. You can see where the CO2, the real hitters are. The real hitters are clearly electricity, for 23 million metric tons a year in the year 2008, and down and below transportation is 1925. Those are the 2 big hitters. But you know, the commercial and residential lighting, etc., is another 500 and some. So there's a fair bit in that too, right? And industrial use is 900. So CO2 is coming from all of these 4 down here on the bottom. Obviously, wind, hydro, nuclear, and solar doesn't give any CO2. And this is what we would like to change. Try to understand how to get rid of the CO2 that's being emitted by those bottom 3. And I just wanted to make sure that if you think about the problem, how bad it is, and if you really want to try to solve this problem. The best estimates of our models today on what will happen by 2050 is if we really want to keep the temperature from rising by about 2.5 degrees Celsius, which is like 4 degrees Fahrenheit, which is not a pleasant idea to have it get that much hotter. You can't emit more than about 1,000 gigatons of CO2 over this 50-year span from 2000 to 2050. Now that sounds like a lot. You might think, well, that's okay. Except that for the last 10 years, we haven't done anything, and the world is still emitting 33 gigatons a year, and that's already 330. So in 1/5 of the 50-year period, we've done 1/3 of the CO2, and so we're running ahead of ourselves. And if you as any physicist would do, to take that nice straight line and try to put a curve on it to make it come out, that only 1,000 was emitted, that you discover that, well, God, you have to reduce the amount of CO2 emissions by a factor of 8 by 2050, and that's a huge challenge, and one that I don't know if we'll make, but it's the one that, you know, Wall Street Journal writes an editorial that says this is ridiculous, right? And maybe it is, but this is just simple mathematics, right? And so we have to face up to it. There's a lot of information on this. I don't want to claim that I'm the world expert on all this stuff, but there's many books, many things, reports have been written on the whole issues of energy. And this one is a huge report that was just done by the National Academy a year or so ago, but there's others that have been done too. So if you want to learn more, there's plenty of places to learn, get the picture of all this. Now I want to go and talk about science instead of talking about the problem. Talk about maybe some solutions here. And my organization believes that many of these problems that we're faced today, besides being political and economic problems, many of the solutions will involve materials. And we believe that we're gradually making enormous progress in the way we do science of materials. And this is one of the things we're trying to put a lot of emphasis on. So from a research point of view, we see our ability to simulate materials and while we're making new materials, we can really change the dynamic. And I don't care if it's photocells, if it's carbon capture, any of the technologies I'll be talking about in a minute, they all grind down to being a materials issue. And whether it's and that's one of the things that you find yourself continuously doing. In materials, the other side of it is biosystems, and we really are pushing very hard on the biofuels issue to try to see if you could substitute for gasoline some kind of a biofuel that's made from not from corn but from other crops like switchgrass and corn stover and that kind of thing, and we'll talk a bit more about that. Anyway, so along with both of those, we do a lot of modeling and simulation, and these are really the kinds of activities we have behind all of the ideas of trying to solve the energy problem. Let's go on. So if we want to really address all the different problems here, you got to sort of attack the whole picture, okay? And so if you look at the whole picture, well, what do you do? Well, what can you do? That's the question, right? And of course, if you get down here to petroleum, well, that's your cars. And what can we do in cars? Well, we can electrify the cars, and that gets rid of the petroleum. But then you have to make, while you're doing that, you have to make dang sure you're not generating CO2 in the power plant. But that pushes the problem to a different place. So we could, but that's called fuel switching, basically, or we can make biofuels. That's the other option down there, and I'll talk about that. And if you really wanted to, in the coal and the natural gas industry, you really have to try to think of some way to capture the CO2 that comes out of the furnace, one way or the other. And that's a subject which I'll talk a little bit about. There's a lot of work on that. And we're trying to figure out how to do that. Of course, we don't have, if we can make those little ones up on top, we could make those things be bigger, and we would in bigger parts of the industry, they don't generate CO2, so they're a good solution. But as you all know, all of this comes down to price, and these various technologies would all be used if they were cheap enough, and each one of these things have a price tag to them. If you want to use all this intermittent stuff, you have to do something about energy storage. You can't You can't use wind and solar without having some other thing that takes up the problem when the wind isn't blowing or the sun's gone down, and so you have to find either a battery storage place or some other natural gas or something that fills in the gap. And we'll talk a bit about that. And as you know, you're going to get a tour today on the whole idea of smart grids. The idea there, of course, is to have much more reliable grid, but also one that's extremely flexible, that can handle all of the intermittency, et cetera, that wind and solar present to it, and also to more efficiently interact with the customer. That's one of the other issues that the smart grid aspect. One other aspect of smart grid is whether between you and the power company, you can make a deal whereby you get a different price during a different time of the day and that kind of thing for electricity. So the whole idea with electric vehicles is that you charge them at night, and the electric company would charge you as much as they charge you in the day, and so you would have a smart meter at your house which would figure out what time of the day you were doing those things, and that's part of the smart grid effort. Finally, you know, in the end, you would like to do a lot more end-use efficiency. We all presumably have gone through the light bulb business, incandescent light bulbs, the fluorescent light bulbs, the solid-state lighting, and we like to walk down that path. But that path is like most of the paths on this chart. It is a question of cost and price, and we've just got to solve some of these price issues. Let's go through this, and I'll talk about the various things a little bit and give you some idea of how we in the research organization think of these things and the kind of things we try to do to make a difference. And I'll give you simple examples. Let's talk first about these things that don't emit CO2 and how we can make them cheaper and better so that they will be acceptable in the industry. And so solar cells and solar photovoltaics are one of the big issues in the industry. And you know, it's interesting. We've driven the price down. We, not just the DOE, but the industry as a whole has been very successful in driving the price down. It had a funny blip in this period here, and it didn't go down continuously to the end point. And the reason it did that is that all of a sudden there was a big expansion in the industry, and there wasn't enough silicon around, crystal and silicon around to make the solar cells. And of course, those people who were making single crystal silicon and could sell it were figuring out that they could make money, and the price went up, and so that's over now. And there's now silicon is dirt cheap, and compared to what it was a few years ago, and so the price now is more on the trajectory we expected it to be on, but it isn't low enough. This is just the cell itself. We are looking at. We believe that if you could, the install price once you use this number for the solar cell. The install price is still about $4 a watt hour, and so if you think about that for a minute, I do it for my house, and I can think in real terms, right? I have electric bills and stuff I can compare it to, and if I take $1 a watt, I can therefore put on my rooftop something like 6 kilowatts worth of solar power. Okay, 6 kilowatts worth of solar power, about right for me. But at $1 a watt, that's only $6,000. My electric bill is $1,400 a year, or something like that. So I make that up in 5-6 years. That's great. Man, that's an economic winner, right? But at $4 a watt, it's $24,000 a year, and that's getting on the edge of whether I believe I can make money on that or not, or come out ahead. And and before that, it was $80. I mean, before that, it was enough that that same 6 kilowatts would have cost you $80,000, and now it's a no-brainer. And the state of New Jersey was trying to help that out by giving you $30,000 back on your $80,000 investment, but that's crazy, right? Let's face it, we can't have that. So we got to improve this, and you know, this is so the technology challenge really is to come up with $1 a watt, and DOE has got a program now which we're trying to work with the with the solar industry to really bring that number to that point. Solar industry claims that by 2015 they'll be at $1.80 something, and we would like to push that down a little further. And I think even at $1.80 they'll be doing okay. But but we need to keep on trying to figure out how to better make higher efficiency cells at an inexpensive cost, and we would claim that there are still sort of fundamental science issues that are involved in trying to make these improvements, and that's my science hat. And in fact, I always love to cite the one that comes from an outfit called First Solar. A friend of mine who's the chief technical officer there, and it turns out that they make cadmium telluride solar cells, and it turns out that the contact, the metal contact that you make onto cadmium, so for you it's a P side, right? You understand that. That contact has a high resistance, and you cannot make a very low resistance contact. And if you have a photocell and you have a high resistance in series with it, it doesn't work very well. And that's the kind of thing that I think there's still some fundamental science left to be worked on here. But we have some really cool things that have happened. There's a fellow we supported at the University of Illinois, actually it used to be at Bell Labs, and named John Rogers, who invented a way of making solar cells, stacked up solar cells, and he could stack up a whole bunch of solar cells on top of one another, and then he had a way of etching them apart, and then he would slip them on. They were small squares, and he would slip them onto a piece of plastic, and you made a very flexible, nice, very high efficient solar cell. And so that all got funded by us and by our applied areas, and now it's a company called Semprius, and they have a bunch of backers that you see over there, and they're hoping to make this into a reality. And so this is the kind of thing we like to see ourselves doing, namely funding the science part of the organization, funding some really good research that leads to something really new, and then our applied areas to take over the funding until it's ready to become something that can go in industry. Now, whether it's a win or not, that's still an open question. It's just started, but it's an exciting new direction we have in solar cells. Let's go on. CCS, this is a big challenge. But ideally, what you'd like to do is you have a coal plant, and you're burning the coal, and the CO2 gets into the flue gas, and the flue gas goes out the chimney. And of course, it just the CO2 goes with it and into the atmosphere. The question is, can you stop that? Well, there's a lot of ways of doing that, but current technology involves amine solutions and sprays of amine that goes into the fuel gas and collects up the CO2, and then you take the amine and you put it. Cool it down and put it in a new vat, and you separate the CO2 from the amine, and then you stick the CO2 in the ground. And that's a standard process today. That takes a lot of energy. It uses something like 25% of the energy of the electricity that is generated by the power plant. So it's not exactly what you'd like to do. and it essentially, as far as I can see, it doubles the price of your electricity. And this country is certainly not in the mode of people who deal with it. Utility commissions will tell you nobody's in the mode of letting the utility companies double the price of their electricity to stop CO2. And so we need other ways of doing this, and I don't know whether we can find them or not, but this view graph just says, look, no matter what you do, you're going to have to do something about CCS, because for the long term, gas and coal are going to be an important part of our energy mix, and so we really do have to solve this problem. And I just remind you that there are different ways of doing this, and one of them is the top one, which is you separate the CO2 as I just described. You take the flue gas that comes out of the furnace, and you have some process which pulls the CO2 out of the flue gas. Now, the problem with that one is that the CO2 is maybe 5% of the flue gas because it's got all the nitrogen still there and still some residual oxygen, et cetera. So you're trying to extract 5% of the flue gas, and you need to extract it with very high efficiency to be effective. It's very hard. That's why it's one of the problems that it is. An alternative, which I kind of like, is the bottom one, and that is, instead of doing that, what you do is you take air and you separate the oxygen from out of the air, instead of getting a pure stream of oxygen. And when you do that, it doesn't really matter if you get all the oxygen out of the air. All you want is pure oxygen. And if you get 10%, half of it, that's good enough, right? And as long as it's enough. And so what you can do there is you separate the oxygen from the air, let the nitrogen, et cetera, the rest of the air go off. They then send the oxygen into the boiler with the coal or gas, and it burns, and you get nothing but CO2 coming out and some water. And so, it's very easy to separate CO2 and water. So you don't have to go through this complicated separation process on the back end of the thing. I think, and right now we have a demo project called FutureGen, which is doing exactly this. And we're anxious to see how that works out. We hope the big issue there, of course, is the cost of separating the oxygen from the air. But it seems to me quite a much simpler way of doing things. But we'll see. The price is not in yet. Anyway, so we're looking at all kinds of other ways in which other kinds of materials that you can separate CO2 from things. And one of the issues, this is an example where it works. One of the big issues in natural gas wells is that natural gas has a fairly large amount of CO2 in it when it comes out of the well. And in order for you to put it in the pipeline, you have to get rid of that CO2. So this is a new material that we think is very promising for separating CO2 in that configuration. So here it shows a feed of natural gas, methane, CH4, which is 20% CO2. It runs through this metal matrix, metal organic framework, and and you can see that as long as it isn't saturated, the CO2 is essentially zero. And so we see that as a new material that we think might be important in the energy industry eventually. But it's a new thing we just worked on in the last few years. The other aspect of CO2 capture and sequestration is the sequestration. You have to shove it in the ground, or it has to stay there. Can't do all kinds of bad things down there. So we've got a program of research in which we're looking at what happens. The CO2 you're going to shove in the ground is actually at very high pressure, and that it's high enough pressure that it's effectively a liquid. So the question is, how does it interact with the rock and the microbes, et cetera, that you're going to run into down there? That's the kind of thing we look at. Just cite a couple things. We learn about that down in many places there's just called nanoporous clay, and it acts very differently. In fact, it's good. It takes up 3 times as much CO2 as regular calcite does, or amorphous calcite. We've learned about how CO2 will react with amorphous calcium carbonate and turn into calcite crystals and give a pathway for better injection. So we're learning things like this. It's very detailed, very complex chemistry that is going to go on deep underground when you shove this stuff in it. Likewise, here's some other things. These guys are doing a lot of model simulations of how this whole process is going to work, and so we're complementing the experimental work with modeling. Let's keep going here. Fuel switching. The obvious fuel switch here is, besides making electric cars, is to do biomass. And we have, in the research area, had created 3 biomass centers. And these centers are a new type of approach to research that we're using here. And that is, we instead of handing out a lot of research dollars to a lot of different professors in the universities, what we've done is we said, okay, we really want real progress on this well-defined applied thing. That is, create a process for making biofuels that is cheap and inexpensive and doesn't use food crops. It's a big problem with ethanol today. It's using corn. The price of corn has gone way up in the last years because of that. And so we definitely don't want to use fuel crops. And so we created these three centers, and the idea was to create a concentrated group of people with very, very strong leadership on the research side that can make decisions in real time and operate in a very different way than most university umbrella grants do. You know, I was at Princeton University before I came to this job, and I remember we used to get a big joint grant for a whole bunch of us, and we'd meet when the grant finally was granted, and we'd say, okay, you get this much, you get this much. 2 years later, we'd come back and say, oh, how are we doing? We got to make a report. We're going to get reviewed, right? But it was not a question of really working together. We were independent professors. Basically, what it boiled down to. This is not meant to be that kind of thing, and it has turned out not to be. In fact, they've done some really cool things, and for instance. This group, the BSAC group, is at Oak Ridge, and they have various collaborators. And one of the collaborators at a place called the Nobel Foundation, and not to be confused with the prize. This one's in Oklahoma, they've managed to take the DNA of switchgrass and change the DNA so that the switchgrass grows with a lot less lignin than normal switchgrass. Now, why is that important? Well, lignin is the molecule that takes cellulose and holds it together and binds it up into really stiff stuff. And if you want to get cellulose and sugars out of grasses, you've got to break down the lignin. So lignin is not easy to break down. So being able to get rid of a lot of the lignin and still have switchgrass that stands up tall in the field is a thing that's very important. And in fact, it's so important that we have found that you can actually make 30% more ethanol from switchgrass with this new switchgrass than you could before. So it's a big improvement. And we're looking very carefully, working with companies that are interested in building plants of this type. And I personally think we're getting close now to a competitive price. And when I say competitive price, I don't mean a price that is subsidized the way corn ethanol is today, but a competitive price that actually could compete in the marketplace in a real way. So we're quite proud of these organizations. Let's go on. I wanted to mention this because this is where I see our research being, and the kind of thing that we need to learn that we don't know yet. You know, in biology research, what's happened over the last 20 years is we have learned how to decode DNA fairly well. We decode something like 13 times a trillion DNA amino acids every year in our facility that decodes DNA. So the biggest problem we have today is we have these huge databases of decoded molecule sequences, and understanding how to do them is an important thing. At the same time, what we have is we have created synchrotrons. We have built a bunch of synchrotrons across this country. They have been able to do protein crystallography in a way that just wasn't possible in the past. And we now have been able to look at the structure of something, the actual arrangement of the atoms, of something like 10,000 proteins. And so we're getting these huge data banks of all this stuff. And now we've got to figure out how to put all this together and understand how things work, right, in cells. And that's where where the biological issues are today, is to figure out better having all that understanding, how does it all come together. And this is a great example of something we've been studying some, and this thing is called cyanophyces, and it's a microbe. And what you do is it has a very interesting life. It gathers in sunlight during the day and CO2, and it somehow or another takes the sunlight and the CO2 and puts it into this thing called glycogen, and glycogen turns into glycerol and interacts with nitrogenase. And during the nighttime, it emits hydrogen and nitrogen. And so the question, how the hell does this thing work? And so that's the kind of question you really are trying to ask today. And it's those kinds of things that you would like to learn about. Anyway, that's just a simple example. And the other thing we're trying to do as an alternative fuel is plants and everything take the sun and convert it into energy. That's what they do, right? Convert it into energy and they grow, right? The question is, can we figure out how to do artificial photosynthesis in a way that is much better than what plants do, and actually create fuel more directly? We created a hub similar to those biofuel hubs that is going to try to address that problem. That is a real challenge, but I think we've tapped into the best biochemists and chemists in the country to drive this, and we'll see how it goes. It's being driven by Nate Lewis at Caltech, and it has participation of other universities and Berkeley Lab. Finally, we have to have electrical storage. We do a lot of work on batteries. The problem with electrical storage on the grid are threefold. You have, very short-term effects when somebody slams off a great big motor of some sort. You have to adjust quickly because one of the things that's very different from a communications grid is the amount of power you put into the grid has to be equal to the amount going out, and so this has to be kept balanced. And so adjusting quickly is a very important thing. Ramping up when you're ramping up a large amount of power or demand. And then, of course, there's the whole business of the peak of the day and how you handle it. And the peak, in most parts of the country where it's hot, the peak is in the summertime around 4 or 5 o'clock in the afternoon, and you have to be able to supply an enormous amount of power. And for example, in California, they have all these windmills out there, but the fact of the matter is the best wind in California is at 4 a.m. in the morning. And so it is not exactly in sync with the peak power needs. And this is one of the problems, and can you find a way to store that energy or something to make it work? And that's all illustrated there on the difference between the red and the blue. Anyway, there's all kinds of proposals that have been made for this kind of thing. There's lots of different ones. We haven't really, none of them have won, as far as I can see yet. It's true that pumped hydro is a really nice solution. This is where you have a lake and you build another lake up high on a mountain somewhere. You pump the water up during the night. You draw it back down during the day, and you compensate for your needs with that. And there just isn't enough places in the United States to do that, and you're not going to do it. And the other really one that is thought to be fairly efficient is actually take the electricity you generate from wind and solar and turn it into high pressure gas that you shove in the ground somewhere, and then later when you need it, you take the high pressure to drive a turbine. And that's called CEAS. And that's another way that seems like it might work. But then there's the whole host of batteries that are aimed at it. There's these flow batteries, which in some sense a flow battery is a battery in which you get a reaction chamber, but you can make them as big as you want, but depending on the tank of materials you have on either side of the active battery. And so you can make them very big if you want. I don't know if people ever go that direction or whether it ever be cheap enough. In any case, we've got a lot of work to do to get the right kind of batteries. And of course, this is all batteries for the grid, and battery for cars is a whole other subject, and much more complicated subject. But this one here, this is an old illustration, but it's still worth mentioning. This is how we have worked in the batteries, and we think it's really quite successful. We funded a person at MIT to do research on batteries, and he did a lot of research on the cathode material. The cathode material turns out to be, in a lithium-ion battery, to be the difficult thing. And he came up with a new material, and he did that on our science research. Then what happened is he got some applied money from applied organizations. He got some money from a small business funding, and next thing you know, he created a company, and now there is this company called A123, and they make lithium-ion batteries for a fairly sizable number of applications. And we've done this again in, oops, wait a minute. We've done this again in recently in another cathode material that General Motors and LG are using in the Volt. And so we invented the material. We did a lot of the early work at Argonne National Laboratory. We licensed the material to General Motors and LG, and they're now going to start producing it. But you know, we do a lot of research in batteries. This is really one of the coolest pieces of research that appeared in Science just recently. And these guys at Sandia National Laboratory and others that worked with them figured out how to make a battery inside of an electron microscope. And an electron microscope, of course, is a vacuum, so it's a little tricky, right? But they figured out how to do it. And a lot of people were talking about using these metal oxides as cathodes, and in fact, nanowires are metal oxides. And so they had some tin oxide metal wires, and they ran this thing as a battery, and the lithium went over to the metal oxide, and the metal oxide started out as a straight rod and ended up like that as the lithium went on. And the problem is that you found out that when lithium goes into tin oxide, it expands it by a factor of 2.5, and so you get a mess. And the bottom picture just shows how it goes into the lithium oxide, into the tin oxide in a wave that propagates down the rod. And so it presents some interesting problems as to how you would ever use that kind of a cathode. So this is just an example of research. Lastly, I'll talk about is fusion and fission, nuclear power. It's of course the real, in some sense, a really important aspect of this thing. We as a department are pushing very hard on what we call small nuclear reactors. Small modular reactors, what we call them. And here's the problem that we see the industry facing. Today, the view is that the learning curve has told us that the bigger nuclear plant you build, the more economy of scale you get. But this has gone on to where people are building nuclear power plants that are 1 billion watts generation capability, or 1.5 billion. These nuclear power plants cost $6 to $7 billion to build. Now, as we were talking about earlier, the utility industry in this country is broken up into lots of companies. Many of them are only $20 billion in total capital value on the market, right? And you ask a $20 billion company if they're willing to make a $6 billion investment. You're asking them to bet the farm, right? I mean, bet the whole company on this one thing. So it's not very likely they're going to do that. So we're trying to see if we can revive the idea of small modular reactors, which instead of a billion gigawatts, a billion watts, it would be maybe 200 200 kilowatts, I'm sorry, 200 megawatts, and instead of, I'll get it right in a minute. and this would be, maybe a fifth of those big power plants. And we think you can build those for maybe $750, $800 million. And that, hey, on a $20 billion base, you can imagine investing, right? And so we're trying to push that. The question is, how do you get away from this economies of scale? And the answer, we hope, is that if we really make these modular, namely to make them in a factory and crank them out and run them out on a truck, that you can make them cheaper. And we have some evidence that is true, in that if you look in Korea today, they have been building the exact same nuclear power plant now to where they built 6 of them. And the price of the sixth one was 40% of the price of the first one. So there is some evidence that you can make the learning curve work for you, is the point. And we, as a nuclear power industry in this country, haven't done that at all. In fact, the nuclear power plants in this country have gotten more expensive, every one that was ever built. The wrong direction completely, right? So we're hoping to do something about that. At the same time, we're doing some research. We're still interested in trying to make a fusion reactor someday instead of a fission reactor, where we take deuterium and tritium and bang them together and get fusion. And you have some research here at Lehigh on that. But we also, believe that eventually gas-cooled reactors will be important. This means you need to worry about high-temperature materials, and I don't want to go into details of this. This is an illustration of how you can make a multi-grained material which can withstand a lot more damage from the radiation in a nuclear reactor than you would otherwise. And I don't want to explain all that right now, but it's an interesting approach. We of course have still, as I say, we're still interested in fusion. We are involved with 6 other countries, if we count the European Union as a country, in trying to build what's called ITER, an international tokamak reactor. And this thing, you have to get a feeling for how big it is. That is a human being down there. So this thing is enormous. It's being built in Cadarache, France, and we're just getting the first buildings built, the big hole for the reactor, and they're all of the 7 countries. I would claim this thing is as much an experiment in international science as it is an experiment in fusion, because it's got India, China, South Korea, Japan, the United States, Russia, and the EU. Now, do you ever think about that set of bed partners? It's very different from, for instance, people talk about CERN and the LHC and CERN. That's a European thing, let's face it. And that's the countries that have common culture. We got a set of countries here that are just totally different. And so it's as much a political and international relations issue as it is a technology issue. So anyway, we hope someday we might have fusion. Heaven knows when. Anyway, that's it. When I talk to students, I always use this as the last view graph, because it seems to me that when I was a young man, the recruiters had this view graph all around every post office in the country, and they wanted you to go join the Navy, the Marines or something, right? And I think the energy crisis the energy issues are the big issue of our era. They're going to be the big issue of the era for the next 20 or 30 years, and I think people are going to have to we're going to have to mobilize this country in a way that's similar to the ways we were mobilized around Sputnik and around World War II and that kind of thing. So anyway, thank you very much.